Hi everyone, I'm Adrian from the Australian Computer Museum, or the ACMS, based here in Sydney, New South Wales, Australia. At the ACMS, we have one of the largest digital equipment corporation collections anywhere in the world. We were founded in 1994 by many people, including Max Burnett, one of the first employees of Digital Australia. DEC was founded in 1957 in Maynard, Massachusetts, and grew to be one of the largest computing companies in the world. In our collection, we have a significant amount of documents, computers, and training material. And today, we're going to present some of that training material to you in the form of old VHS tapes. So, please sit back, relax, and enjoy. Thank you.
Unit 4 presented an overview of the VMS operating system and introduced the components that allow users to share the CPU and main memory. In Unit 5, we'll look more closely at the mechanism that makes user interaction with VMS possible. This mechanism is called a process. This unit contains 2 lessons. Lesson 1 describes the structure of a process, including the virtual address space, the hardware context, and the software context. Lesson 2 examines the types of process that VMS can create and how they relate to the concept of a job. It also presents the system services used for process control and communication.
A process is the fundamental scheduling unit in VMS. A process, rather than a program or an image, is scheduled and thus gains control of the CPU. Let's take a look why. As you remember, a source program is a sequence of instructions in a computer language that logically expresses the way to solve a problem. Programs, even those written in assembly language, are not machine executable. An image is the machine executable form of a program. An image is the form the source program takes after it has been compiled and linked. You might wonder why images aren't scheduled in VMS. One reason is there would be no way to distinguish between users when they are executing the same image. Consider a situation in which 2 users are simultaneously running a text editor. Each user employs the same image, but each obtains different results. The operating system must have some way of distinguishing between these different users. VMS uses the process to define the environment for an image. When users first log in, VMS creates a process for each user. Initially, there is no image associated with the process. A process is the environment in which users can do their work, whether the work consists of writing, running, and debugging programs, or using an application program such as a spreadsheet. A user's process includes information such as the user's identification, privileges, and the use of system resources such as memory. When a user brings in an image for execution, the image executes within an environment, the process. So if 3 users are using a text editor, they are using the same image, but the environment in which each image executes is different. When an image executes, it is said to execute in the context of a process. Process context is what distinguishes one image from another. VMS manages and allocates system resources such as CPU time, memory, and I/O devices to processes rather than to users or images. Let's take a closer look at the parts that make up a process. A process consists of 3 components: a virtual address space, a software context, and a hardware context. These 3 components define the environment in which an image executes. Let's look at each in turn. The first component of a process is the virtual address space. In a virtual memory system, main memory and auxiliary storage are combined to give the illusion of an almost unlimited physical memory. With virtual memory, the user sees a vast number of virtual addresses, the virtual address space, which can be used just as if it were physical memory. A portion of this virtual address space is reserved for image execution when a process is created. How then does this virtual address space relate to an image? A virtual address is assigned to each instruction and item of data in a program when a program is linked to create an image. As an image executes in the CPU, virtual addresses are used to identify instructions or data to be operated on. A virtual address does not refer to actual physical locations in memory. For example, information the image thinks is stored in virtual location 200 is not actually in that physical location. Rather, the information is stored in some other location in memory, or the information might reside on disk storage. The operating system is responsible for keeping track of where that information is really stored. The mechanism for this is called mapping. Mapping allows the system to translate virtual addresses into physical addresses. Because each process has associated with it a set of virtual addresses that are uniquely mapped to physical addresses, address space is defined as part of the context in which an image executes. Hardware context is another component of a process. The hardware context is simply the contents of certain processor registers. For example, there is the program status long word, PSL, the program counter, PC, the stack pointer, SP, the frame pointer, FP, and the other general registers. There are also several additional special processor registers. The image refers to and manipulates the contents of these registers, but the contents are not part of the image. The register contents are part of the environment, specifically the hardware context. As long as an image is executing, its hardware context is contained in the processor registers. There's only one set of CPU registers, so when another process is scheduled, its associated image will need to use the CPU registers. Thus, VMS needs a way to preserve the register values for a process when it must give up the CPU. To store these register values, VMS uses a data structure called a hardware process control block, or hardware PCB. Let's take a closer look at the hardware PCB. It is used to store the contents of the processor's registers when the execution of a process is interrupted. The stack pointers are 4 registers corresponding to the 4 processor access modes: kernel, executive, supervisor, and user. R0 to R13 are the general registers discussed earlier in this course. They can serve as temporary storage locations for data that the CPU is operating on, or they can contain addresses of data stored elsewhere in memory. The program counter, or PC, contains the address of the next instruction to be executed. It indicates the instruction at which the process should resume operation when it regains control of the CPU. The processor status long word, or PSL, contains several items of data relating to the overall status of the CPU when the execution of the process is interrupted. Finally, the base and length registers describe data structures that map the virtual address space used by the process. Each process has its own hardware PCB, which contains the hardware context of the process. When the CPU switches from one process to another, the hardware contexts are switched. This operation is called context switching. The register values for the outgoing process are saved in its hardware PCB, and the values contained in the hardware PCB of the incoming process are loaded into the registers. Later, when the first process regains the CPU, the registers will be reloaded with the values saved in its hardware PCB, so the image can continue executing with the correct information. You'll find further details about context switching in the next unit. So, the hardware context represents the state of the processor registers during the execution of an image. The software context contains information such as privileges, limits, quotas, and priority, which define rules that an image executing in the context of a process must obey. The system manager enforces many of these rules by defining a record for each user in the user authorization file, or UAF. The UAF describes the user's privileges, limits, quotas, and priority level. A privilege indicates if a user is allowed to do something. For example, one privilege indicates whether a user may use a network service such as set host. The privilege mask is a data structure which consists of 64 privilege bits that define the set of privileges for a particular user. A limit is defined as a ceiling on the number or amount of a reusable resource, for example memory, that a user may have. A quota is similar to a limit, except it represents a ceiling on the amount of a non-reusable resource, such as CPU time. The system manager also defines a priority level which serves as a basis for scheduling each user's processes. Simply put, VMS schedules processes based on priority. When 2 or more processes are competing for CPU time, the process with the highest priority gains control of the CPU. Privileges, limits, quotas, and priority are all defined for a user when the system manager creates a record in the UAF. When a user logs onto a system, part of the UAF record is copied into the software context of the user's process. To understand the significance of software context, suppose two processes are executing the same image. One process has a priority level of 4, and the other's priority level is 2. The priority level is part of the software context of each process. The process with the highest priority is scheduled first, and therefore gains control of the CPU. The image for both processes is the same, but the differing software context determine the order of execution. As with priority, such things as privileges, limits, and quotas are part of the software context, not part of the image. Just as the hardware context has a data structure, the hardware PCB associated with it, so does the software context. The software context is maintained in two major data structures: the software process control block, or PCB, and the process header. Each process has its own software PCB and process header. Why is it necessary to have two separate data structures for the software context? Since memory is a limited resource, all of the data structures associated with all processes can't fit in memory. Some processes must be removed from memory and held in disk storage until the process is ready to execute. If this is the case, the process is said to be swapped out of memory. When a process is swapped out, some of its software context must remain in memory. VMS needs a way to identify when and how to swap the process back in. A data structure called the Software Process Control Block, or Software PCB, meets this need. It contains just the minimum information about the process that allows VMS to decide when to swap it back into memory. The software PCBs for all active processes are always resident in memory. They are never swapped out to disk storage. VMS needs several categories of information in order to determine when to swap a process back into memory. Most of this information will be discussed in later units. The remaining software context is contained in the process header. This data structure holds all of the software context which is not essential to whether or not a process should be swapped into memory. Some of the major components of the process header include the privilege mask, the hardware PCB, quota information, and certain page tables. The privilege mask, as mentioned earlier, determines which privileges the process may use. When a user initially logs onto a system, the mask is obtained from the user authorization file. Quota information is also obtained from the user authorization file. The hardware process control block representing the hardware context of the process is kept in the process header. The process header also contains data structures called page tables that are needed to map the virtual address space used by a process. You'll learn more about these page tables in the sharing memory unit. The address of the process header found in the software PCB is the link between the two data structures associated with the software context of a process. The address is kept in the software PCB because VMS must be able to quickly locate the process header in order to swap the process back in. To summarize, a process contains three components that support the execution of an image. The virtual address space contains all the virtual addresses the process needs to reference instructions and data to be operated on. The hardware context represents the contents of the CPU registers as the image executes. The hardware context is stored in a hardware PCB when a process gives up control of the CPU. When a process is ready to resume execution, the process's hardware context is loaded from its hardware PCB. While the hardware context represents information about what images are doing in the CPU, the software context defines what images are allowed to do. Privileges, limits, quotas, and priority level are part of software context. Two data structures hold this information. The software process control block always remains in memory. It is never swapped out to disk storage because it contains information which is essential in determining whether the entire process should be memory resident. The process header may be swapped out to disk storage to conserve memory space. The process header contains information including the hardware PCB. The information that's kept in the process header is not essential to determining whether a process should be swapped into memory. The two data structures are linked by a pointer in the software PCB to the process header. This brings us to the end of Lesson 1. Please read the information in the course reference guide and complete the exercises. In Lesson 1, we describe the structure of a process. In this lesson, we'll examine the different types of processes, the concept of a job, and some of the system services available for process control and communication. Let's start by taking a look at the different types of processes. Many applications are designed to use a single process. Other applications are designed to use multiple processes. When multiple processes are used, one process often creates sub-processes to do specialized tasks or activities. An owner process is a process which creates a single sub-process or a number of sub-processes. Thus, we can speak of an owner process and its sub-processes which do specialized work. For example, an airline reservation system may use one sub-process per user to handle terminal I/O. A sub-process may create its own sub-processes. It is quite possible to have a hierarchy of owner processes and sub-processes. Whenever an owner process terminates for any reason, all of its sub-processes must terminate also. A process which has no owner is called a detached process. For example, when a user logs onto the system, a detached process is created for the user. A detached process, together with all of its sub-processes, is called a job. In VMS, a job is the basic accounting unit, while a process is the basic scheduling unit. All of the processes in a job share some of the resources that were initially allocated to the detached process at the top of the hierarchy. A portion of a user's record in the user authorization file defines the job's resource limits and quotas. These limits and quotas are used to define ceilings on the use of resources such as the CPU, memory, and I/O devices. For example, there are limits and quotas that control the total processor and connect time usage, the number of sub-processes a job can create, and the number of simultaneously open files. The limits and quotas are part of the software context of a process that is often swapped out of memory. They are stored in a data structure called the job information block, which is part of the process header. A job, not a process, is considered the basic accounting unit in VMS because the detached process gives a portion of its resource limits and quotas to its sub-processes. The process, however, is the basic scheduling unit because each process is scheduled independently of the others. All the processes in a job compete with each other for control of the CPU, just as they compete with all other processes outside that job. A job is either referred to as a simple job or a complex job. A simple job is a single detached process. The process is created by the operating system on behalf of the interactive user who logs in at a terminal. Or the process is created for the purpose of executing a batch job. A simple job has no sub-processes, and images execute serially within it. For example, when a user logs on the system at a terminal, VMS creates a detached process for that user. If the user edits a file to create a program, the editor image executes in the context of that user's process. If the user then compiles the program, the compiler image executes in the context of the same process. Since there is only one process in a single job, images must execute one after another in serial fashion. In contrast to a simple job, a complex job is one in which a detached process creates sub-processes in which designated images execute. As you've seen, these sub-processes can also create their own sub-processes. In a complex job, several images may execute concurrently. For example, suppose one workstation application uses 3 processes to graphically represent a complex mathematical function. Each process is responsible for performing a portion of the application. One process is responsible for 3 display windows, a window which plots the results of the calculation, a window which shows the status of various components of the application, and a window which allows the user to manipulate the graphic or to request the plotting of another graphic. Another process performs the compute-intensive calculations required by the mathematical function. The final process maintains a database of calculations which are frequently employed. This saves the application from having to recalculate the entire function from scratch each time. Within the context of this job, we can say the images associated with this process execute concurrently. This is not to say that the images execute simultaneously, since only one image can execute at a time. However, as soon as one of the processes gives up the CPU, one of the others is probably ready to execute. VMS offers various system services to control processes and facilitate communication between processes. These services are especially important for complex jobs involving a number of processes. System services are available to provide control over other processes by enabling a process to create and delete subprocesses and to hibernate or suspend a process and then reactivate it later. In a complex job, it is necessary for a detached process to create subprocesses. A number of system services are available to a user to create subprocesses. The system manager grants the privilege of using these system services. The number of subprocesses a job can create is a resource limit, also determined by the system manager. When a process creates a subprocess, it can grant the subprocess all or some of its privileges. A process can also grant some of its resource limits and quotas to its subprocess. One class of resource limits are subtracted from the totals available to the owner process when they are used by a subprocess. Examples of these resource limits are the number of open files and the number of subprocesses which can be created. These resources are added back to the owner process totals when they're not being used by a subprocess. A portion of one granted quota, CPU time, is subtracted from the owner's quota when a subprocess is created. It is only returned to the owner process when a subprocess is deleted. A subprocess may be deleted when it has completed its work. When a subprocess is deleted, resource limits of its owner are all restored. The hibernate and suspend system services are also ways to control a process. They allow the user to place the process into a wait state until it's needed. Use of these system services can be especially efficient in real-time applications. For example, a flight simulator may require turnaround times in the 25 to 50 millisecond range. One way to enhance processing speeds is to design some portions of the application as separate processes. Those processes which perform the basic flight simulation functions, such as flight motion equations and graphics, can be designed as a group of hibernating processes. A process is capable of being immediately reawakened as required by the student's actions. Since the images are ready for execution, there is very little delay in reactivating them when necessary. Let's contrast hibernation and suspension, the two ways of temporarily halting the execution of a process. A process in hibernation is reactivated by the wake system service. On the other hand, a process in suspension is reactivated by the resume system service. A process can only cause itself to hibernate, while a process can suspend itself or another process if it has the appropriate privilege. However, the key difference between the two methods is that suspension is a more pronounced state of hibernation. A process in hibernation is more likely to be memory resident because suspended processes are the first processes selected to be swapped out of memory. Therefore, a process in hibernation is likely to execute sooner than a process in suspension. A process in hibernation can wake itself and can schedule a wake-up at an absolute time or at a fixed time interval. A process in suspension is more limited in that it can't resume itself and it can't schedule resumption. Both hibernation and suspension temporarily halt the execution of a process. The use of one method over the other will depend on the nature of the application. In addition to providing services to control other processes, VMS provides services for processes to communicate with other processes. Four mechanisms that cooperating processes can use to communicate include the mailbox, global section, lock manager, and common event flag. These mechanisms allow processes to share common data, send messages, and synchronize execution. A mailbox is a virtual device used for communicating between processes. It's classified as a virtual device since it is software implemented as opposed to being a hardware device. The mechanism is called a mailbox because it's used to store and pass information like a real mailbox in which letters are placed. The information may take many forms, including status information and messages. A process, such as Process A, may use a system service to create a mailbox and then insert a message in it by issuing a write to the mailbox. Later, another process, process B, may remove the message by issuing a read to the mailbox. Since a read operation to a mailbox removes the message can only be read one time. When another message arrives, it is queued in order of arrival. A process retrieving a message reads the oldest message in line, or if there is no message in the mailbox, it waits for the next message to arrive. There are system manager-defined and process-defined limits placed on a mailbox and its messages. The system manager defines limits on the size of a mailbox and its messages. When a process uses the system service to create a mailbox, the process defines the maximum size of a message and the maximum number of messages that the mailbox can hold. The use of a mailbox is sometimes restricted by limits on the size of messages and the fact that a message placed in a mailbox can only be read once. A global section is often used to overcome these restrictions, particularly when processes need to share large amounts of data. A global section is a disk file or a portion of a disk file that can be brought into memory. The location of this information in memory allows several processes to quickly access it. Since data may be placed in a global section by one process and manipulated by another process, global sections are often used for inter-process communication. In contrast to a mailbox, where a message can only be read once, information in a global section can be accessed repeatedly by different processes. However, special efforts need to be made to synchronize access to data in a global section. Thus, the use of a global section requires more programming effort to utilize than other system services. The VMS Lock Manager is often used to synchronize access to a global section. In general, the Lock Manager is used when two or more processes share any resource. A resource is defined as any readable or writable entity on the system. Some examples of resources are global sections, files, data structures, I/O devices, and databases. If access to a resource cannot be granted immediately, a queuing mechanism is provided for a process to wait until it can be granted access to the resource. The Lock Manager does not actually allocate or control access to a resource, such as shared files on a disk. Instead, it allows you to assign a name to each resource and store it in a common namespace. The Lock Manager stores resource names in a common namespace and regulates access to those names. When a process is granted access to the resource name, it may then access the resource itself. Again, the Lock Manager does not directly control access to the resource. Therefore, a non-cooperating process can access the resource independent of the Lock Manager, as the process is doing here. For the Lock Manager to be effective, this situation should be avoided. The Lock Manager provides a number of lock modes to control how the resource is to be shared with other processes. Take as an example, three processes sharing a data structure they agree to call database. The name of the resource, database, is placed in the common namespace. Process A places a read lock on database, specifying that it would like to read the resource. It is then granted access to the resource. The lock also specifies that other processes are allowed read access but not write access to database. Process B places a lock on database to gain read access and is granted access. However, if Process C tries to place a lock on the resource name for write access, it will not be granted. The lock request from Process C is placed in a queue where it waits for write access to be allowed to database. In this case, the Lock Manager is synchronizing access to a resource called database. But the Lock Manager can be used as a communication mechanism to synchronize access to any resource, including a global section. While a global section allows several processes to communicate by sharing large amounts of data, a common event flag allows several processes to share a single bit of data. An event flag is a status bit used for posting an event, such as an I/O completion or an elapsed time interval. Event flags are organized into 32-bit clusters. A process may request the use of two common clusters. A process can set, clear, and read individual event flags, as well as wait for one or more event flags to be set. Common event flags are typically used as a synchronization tool for two or more processes. Consider two processes, Process A, which collects data from a seismograph, and Process B, which interprets the data collected by Process A. An event flag is used as a signaling mechanism. Initially, the flag is cleared. It will be set to indicate Process A has finished collecting a set of data and that Process B may start its interpretation of the data. In order for both processes to access the event flag, which is in a common cluster, they have to associate themselves with the cluster. This is accomplished by using a system service. Initially, process B is placed in a wait state until the event flag is set. Process A starts its collection of data. When process A finishes the collection of a set of data, it sets the event flag, signaling B to begin interpreting the data. While a common event flag such as the one used here is used for inter-process communication, a local event flag may only be accessed by a single process. Each process has 2 local event flag clusters available for its use, each containing 32 event flags. 8 flags in the first cluster are reserved by the operating system. A local event flag is an extremely efficient means of starting up or synchronizing procedures within a single program. Like common event flags, they are used for indicating that an event, such as an I/O completion, has taken place. Another system service used for event notification within a process is the asynchronous system trap, or AST. An AST is used when a process needs to execute a routine whenever a condition occurs, such as a certain time of day. An AST routine is like a subprogram in that it is established by the main program. It is different, however, because it is called asynchronously by the operating system via the delivery of an AST, not synchronously by the main program. Consider a situation in which a program specifies an AST routine for terminal input. Now suppose the main program is running. When terminal input occurs, the operating system declares an AST. Upon delivery of the AST, the operating system interrupts the main program and executes the AST routine. An AST is independent of the progress of the main program since the interrupt occurs asynchronously with respect to the program's execution. ASTs as well as event flags are often used in conjunction with a system timer service. A system timer service is used to schedule program activities based on clock time. A process can request notification after a specified time interval. For example, a process can ask the system to notify it in 10 seconds. Or a process can request that it be notified at an absolute time, such as Thursday at 9 a.m. Let's see how system timer services can be used in conjunction with an AST. Suppose a programmer defines an AST routine to periodically update the balances of all accounts, reflecting deposits and withdrawals made since the last update. The programmer issues a system timer call specifying delivery of an AST at a fixed interval, say every 5 minutes. The call also specifies the name of the AST routine to execute upon delivery of the AST. The main program, which calculates accumulated interest, begins running in the CPU. After 5 minutes, the timer expires and an AST is posted, interrupting the execution of the main program. The AST routine now executes, updating the balances of accounts in the bank. Control is returned to the main program upon completion of the AST routine. Now, let's look at an example in a laboratory setting which shows how the various inter-process communication facilities can be combined. The application is designed to utilize 4 processes. Process A periodically collects data from an experiment. Process B analyzes the data and writes the results of the analysis to disk. If the analysis indicates the need for additional control of the experiment, Process C adjusts the parameters of the experiment to bring it back within the range of acceptable conditions. Process D prints out reports based on the condition of the experiment and the data collected. Process A periodically samples a laboratory experiment under control of the system timer. The timer signals Process A to collect data by means of event flag 1. Initially, the flag is cleared. When the timer expires, event flag 1 is set, and Process A collects data from the experiment. Process A then writes its data into a global section. A global section is used because it is an efficient mechanism for sharing data with Process B, which analyzes the collected data. Process A notifies Process B by means of event flag 2 that the data has been written to the global section. Process B proceeds to analyze the data. When the analysis is complete, Process B writes the results out to a disk file. If Process B determines that the current data indicates the need for additional control of the experiment, it writes a message to a mailbox. Process C reads the message in the mailbox. Process C, alerted by the message from Process B, reads the information in the global section and adjusts the parameters of the experiment. Process C also sets event flag 3, telling Process D to print a message for the researcher that corrective action was needed and was taken. Under normal operating conditions, Process D is periodically invoked by the timer to print out a summary report based on experiment data. Process D is notified to print the report by means of event flag 4. Now, let's review some of the key points in this lesson. When a user logs in, a detached process is created. In turn, a detached process may create other processes called sub-processes. A job consisting of a detached process and any of its sub-processes is the basic accounting unit in VMS. A job, rather than the process, is the accounting unit because a detached process shares its resource limits and quotas with each of its sub-processes. A job can be referred to as either a simple job or a complex job. A simple job consists of a single detached process, while a complex job consists of a detached process and its sub-processes. In a simple job, images execute in a serial manner because there is only one process. In contrast, several images may run concurrently within the context of a complex job. There are several system services available to control processes and facilitate communication between them. System services enable a user to create and delete sub-processes and to hibernate or suspend a process and then reactivate it later. Both hibernate and suspend system services temporarily halt the execution of a process by placing it in a wait state until it's needed again. Suspended processes are often swapped out of memory, and there are fewer mechanisms to awake a suspended process. A number of system services are also available to facilitate communication between processes: the mailbox, global section, lock manager, and common event flag. A mailbox is a virtual device used for communicating between processes. One process inserts a message into the mailbox, and the second process removes it. A global section is a disk file or portion of a disk file brought into memory. The location of the data in memory provides a mechanism for several processes to quickly access and share the same data. The lock manager is used to synchronize access to a resource. It stores resource names in a common namespace and regulates access to those names. A common event flag allows several processes to share a single bit of data. It is often used for posting an event, such as an I/O completion or an elapsed time interval. Inter-process communication is facilitated by system services such as the mailbox, global section, lock manager, and common event flag. On the other hand, intra-process communication, or communication within the context of a single process, is often achieved by a local event flag, an asynchronous system trap, or a system timer service. A local event flag is often used to start up or synchronize the work of a single process. Like a common event flag, it is often used to indicate that an event, such as an I/O completion, has occurred. An asynchronous system trap, or AST, is used when a process needs to execute a routine when a specific condition occurs. When an AST is delivered, the main program is interrupted and an AST routine is executed. An AST, or event flag, is often used in conjunction with a system timer service. Several services are used to schedule program activities based on clock time. System services, whether used for inter-process communication, intra-process communication, or for control of other processes, are often used by programmers to facilitate application development. This completes Lesson 2. Now turn to your course reference guide and review the study material and complete the exercises.